I welcome you all in this lecture on introduction to optimization, and this sub module is part of the modeling and simulation of dynamic system course which you are going through. In the last slide where we have last lecture which was on the system identification, we have seen that while identifying the system, dynamics of the system, many times we require in identifying various parameters, okay, and one of the way of finding out those parameters could be the optimization. So, next two lectures we will be looking at the optimization method in general and some specific optimization techniques which could be used in the whole exercise of modeling and simulation of the dynamic systems. So, optimization, if we talk about a basic definition of it, then it is the mathematical process of obtaining the best result under given circumstances. Okay. Why mathematical? Process could be anything, but as far as engineers are concerned, we use mathematical tools, okay, in order to get the best results under given circumstances. Now, in many activities, engineering activities such as design, construction, maintenance of engineering system, we take so many decisions, okay, and aim of these decisions is to say either we want to minimize the cost in order to make things economical, or we want to maximize the profit, okay, so that company financial health is good and it is able to run, okay. So, the aim here is either minimization of the cost or the maximization of the profit. So, what I want to say is that the aim is either minimization of something or the maximization of something. So, as I was telling you, if you want to ask the definition for optimization, then I can give that optimization is defined as the mathematical process of obtaining a set of conditions that gives the maximum or minimum value of a function, okay. So, here the things which you need to note is obtaining the set of conditions. So, the optimization process is basically getting these set of conditions, and these set of conditions result in the maximum or minimum value of a function, okay. And as you know that a maximization can always be converted into a minimization, okay. For example, if I have to maximize say some function dx, then I can always write as minus of minimization of minus dx, okay. So, this way we can treat any problem as the minimization problem, because if some maximization problem is there, that problem can be written as a minimization problem. So, the tools, optimization tools are usually developed for the minimization problem, okay. So, the optimization problem can be taken to be a minimization problem always. Now, the optimization has got number of applications in engineering design, okay. Say if you talk about designing of aircraft and aerospace structure, we know that aircraft or aerospace structure has one of the principal constraint as the minimum weight, okay. So, if the weight is minimum, they can take the maximum amount of payload. okay. And so the minimization of the weight could be one of the optimization criteria for the aircraft and the aerospace structure. Similarly, if I talk about say other mechanical components, say if it is a cam or gear or linkages, the optimization problem could be the design, optimal design, okay. So optimal design for the these mechanical components, okay. Now if say I am talking about design of material handling equipment in an industry, okay, say conveyors if I am talking about, or belt I am talking about, then the aim could be the minimization of the cost, fine. And if I am talking about say components such as pump, okay, or turbine, or if I am interested in heat transfer equipment such as heat exchanger, then here the aim could be the maximum efficiency, okay. And say if I talk about some structure in the civil engineering domain, say if I am talking about bridges, foundation, then of course the aim of the optimal design could be minimization of the cost, okay. So these are few examples which I have listed where engineering application of optimization can be there. Of course, there are many more which I have not listed here. Now, how does the optimization problem looks like, all right. So, if we talk about optimization problem, so as I said, the optimization problem is to find out a certain set of variables which either maximize or minimize an objective, okay. So mathematically if I want to write it, then the optimization problem could be stated as say finding out a vector x, okay, and this component could be x1, x2 till xn. So optimization problem is finding out of these values of x which minimizes fx. So as I said, maximization problem can also be converted into minimization problem. So we will be talking about only minimization problem, okay. So it is the finding out of these n number of variables, okay, x1 to xn which minimizes fx, okay. So this is the optimization problem. Of course this could be subjected to, that is these design variables could be subjected to certain constraint, say Gj(x) should be less than or equal to 0 for say j is equal to 1, 2, 3, 4 till m, okay. And say so this is one set of constraint. We can have another set of constraint. I will come back to this on when I will talk about the type of constraints. Ljx could be equal to 0 where j is again 1, 2, 2 say till up to p, okay. So these two are the constraint amongst these variables, okay. Here x is n cross 1 which we call it as the design vector because we are interested in finding out these vectors, okay. And fx, this fx we call it as the objective function, okay. And gjx here as it involves an inequality sign, here these are called inequality constraint, and this Ljx is equal to 0 as here it involves an equal sign. These type of constraints are called equality constraints, okay. And n here, these n are basically the number of variables, okay. and as you can see from here, these M and P's are basically the number of constraints. Okay. And these type of problems where we have that is the design variable is subjected to certain constraints, this type of problem is called the constrained optimization problem. Okay. So, the constrained optimization problem have the constraints in them. Okay. Now, there could be the problem which do not have the constraints, okay, and these are called unconstrained optimization problem. Okay. And it could look like this, that is, find x, say x1 to xn, these are our design variables which minimizes the objective function fx. Okay. And here there are no constraints. So, we call it as the unconstrained optimization problem. Now, let us define and explore whatever variables or whatever parameters has been associated with the optimization problem. So, first and the principal one is the design vector. Okay. As the aim of the optimization problem is to find out the value of the optimal value of the design vector which minimizes your objective function. So, an engineering optimization model consists of parameters whose numerical values are to be determined in order to achieve the optimum design. Okay. And these parameters are what we call it as the design variables. Okay. So, say these parameters could be, say, size, weight of the part, number of teeth in a gear, number of coils in the spring, and so on. And when I am writing these design vector collectively together in a vector form, this is what is called as the design vector. When I am writing the design variable in the collective form, it is called the design vector. For example, if say I talk about say the 2 gear teeth, okay, 2 gear teeth in mesh, that is, say we have a situation like this, that is, we have a gear teeth and we have, say, another gear teeth, okay, and when they are in mesh, okay. So, here suppose these are the number of teeth T1 and T2, and say B is the say width of the teeth. Okay. So, if B is the width of the teeth, then this is what we call it as the design variables. So, B, T1, T2, these are the design variables for the gears. Now, design constraints. Okay. So, these are the mathematical functions which define the interaction between the design variables. Okay. So, these constraints, design constraints, are written in terms of design variables. Okay. So, as I define it, they basically represent the interaction between the different design variables. Okay. Any acceptable set of design variables should satisfy these constraints. Okay. And these constraints could be, say, inequality constraint or equality constraint or the site constraints. Okay. So, we will have a look at what type of constraint these are. So, the inequality constraint actually they ensure safety against a failure mode, okay, or satisfactory behavior under the given loading condition. Okay. So, these type of constraints in engineering design are called inequality constraints, and they are written usually say Gj(x) greater than or equal to 0 for j is equal to 1 to m. Okay. So, in general they are written like this, or they could also be written as less than or equal to. Okay. So, those type of representation can be given for the inequality constraints. Then we have the equality constraints, and these type of constraints must be satisfied for design to be acceptable. Okay. And these set of constraints are of this form, say Lj(x) is equal to 0, where j varies from 1 to or j can have values 1 to 2 say till p. Now, example for this equality constraints could be given from the structure mechanics problem, okay, where basically the constraints can be represented like this. Here we know that the K is the stiffness matrix, P is the displacement vector, V is the displacement vector, and P is the load. So, this type of constraints which involve the equal sign are called equality constraint. Then we have the third type of constraint, that is called the side constraint. Okay. Here upper and lower bounds on the design variables, these are referred as side constraints. Okay. These constraints are also known as the geometry constraint, and example could be the upper and lower bound on the number of teeth in a gear mesh. Okay. So, these are what we call as the side constraints. Then we have after seeing the design variable and the constraints, next is the objective function. Okay. Now, a function for which an extremum, and extremum as I said it could be minimum or maximum. In fact, we can convert the maximum into a minimum problem as well, is sought. Okay. So, a function for which an extremum is sought in the optimal design process, that function is called the objective function. Okay. There is another name which is used in literature, and that is called the merit function. Then usually say weight or cost or volume of structure are chosen as the objective function. We could have other objective function as well. Then let us have some idea about design space. This design space is basically defined as the total region or the domain defined by all design variable in the objective function. Okay. So, the total region or domain defined by all the design variables which are there in the objective function is called the design space. Okay. And this design space is limited to constraints. Okay. Otherwise, we may have unbounded design space. If there are no constraints, we will have the unbounded design space, and for which of course no feasible solution may exist. Okay. And as you may be knowing, as the constraints increases, our life becomes easier in the sense that the number of solutions keep on reducing. Okay. So, that way it is good for the decision process. So, here if there is no constraint, we have unbounded design space, then there will be no feasible solution may exist. Constraints are useful, as I said, in restricting the region in which the search for minimum or maximum design variable to be done, and that way it helps us in finding out the optimal solution. Then the local and global maxima. Okay. To explain you this concept, the local and global maxima, actually suppose we have a certain function f(x) and say if we plot x here, then suppose the value of f(x) is something like this, say this is point A, B, C, D. Okay. So, we can see that this A f(x) value at A is highest near to the proximity of this one, near the proximity of A, this value is highest, and so this we call it as the local maxima. Okay. Similarly, here the B value is highest, so this is again called the local maxima, and C value is highest nearby, so this is called local maxima, and this is called the local maxima. But among these local maxima, D has the highest value, so we will call this D as the global maxima. Okay. So, the local and global maxima, the point in design space that is higher than all other points within its immediate vicinity, and this is what is called the local maxima. Okay. And the highest of all local maxima is called the global maxima. Now, let us try to see how can we classify the optimization problem. So, till now we have seen how to define an optimization problem and what are the factors associated with the optimization problem, such as objective function, design variables and the constraints. Okay. Again, constraints are three types, that is the that is the site constraints and inequality constraint and equality constraints. Okay. So, after defining the optimization problem, now let us see the classification of the optimization problem. There are various ways of classifying the optimization problem. Okay. And these classifications are not meant to be mutually exclusive, but to describe the mathematical characteristic possessed by the problems. First classification is based on the type of constraints. Okay. So, the optimization problem is said to be unconstrained problem, optimization problem if there are no constraint, or it could be a constrained optimization problem if one or more conditions are present or one or more constraints are present, then we call it as the constraint optimization problem, and if there are no constraint, then we call it as the unconstrained optimization problem. Then number of independent design variables. Okay. Based on this we can classify an optimization problem. So, we can have a single variable optimization problem and the multivariable optimization problem. In case of single variable optimization, the objective function is function of one variable and of course constraint. Okay. And in case of multi-variable optimization problem, objective function is going to be function of two or more number of variables. Then other classification could be time dependent or not. Okay. So, if your in case of optimization problem, static optimization problem, dependence on time is not there, okay, and in case of dynamic optimization problem, dependent on time exist. Then what type of data are available, okay? So it could be a deterministic optimization problem where the data are known with certainty, okay, and it could be a stochastic optimization problem where data is not known with certainty. Then we could have classification as number of objective functions, okay. So we could have a single objective programming problem, okay, that is we have a single objective function, and we could also have the multiple objective programming problem where we can have the multiple objective functions to be there. Then classification could be the nature of equations involved, okay, and based on this classification it could be a linear programming problem or it could be a non-linear programming problem, okay. So the linear programming problem, there is a unique objective function, and whenever a decision variable appears in either in the objective function or in one of the constant function, it must appear only as power term with exponent of 1, okay, that is it should be linear and possibly multiplied by a constant. No term in the objective function or in any of the constant can contain product of the decision variables, okay. So product should also not be there. Then the coefficients of the decision variables in the objective function and its constraints are constant, and the decision variables are permitted to assume fractional as well as integer values. So this is what is there in case of the linear programming. Then we may also have the non-linear programming. In this case, if any function among objective function or the constraint, okay, if they are non-linear, then this type of problem we call it as the non-linear programming problem, okay. And remember, for every type there are different tools available which could be used for the optimization problem, finding out the optimal value of the decision variables and or design variables which could either minimize or maximize your objective function. So this is all which I wanted to tell you in this lecture. You can have further reading on a very good optimization book, that is Engineering Optimization by S.S. Rao, okay, and next lecture we will see some examples of the optimization problem. Thank you.